A single subatomic particle can carry the energy of a fastball pitch. These are cosmic rays, and they are not beams of light, but high-energy bullets from deep space, striking our planet every moment. Some of them hold secrets so profound, they force us to question the very laws of physics. By the end of this journey, you will know the 25 most baffling cosmic ray mysteries that have left the world's top scientists utterly stumped. How can a particle from an empty void of space hold more power than our greatest machine? What does a cosmic blast from over a century ago have to do with these invisible messengers? The answers redefine our place in the cosmos. What do you think is the universe's most powerful particle accelerator? That single particle, carrying the kinetic energy of a professional fastball, has a name. Scientists call it the Oh My God particle. It was detected in October 1991 by the Fly's Eye Cosmic Ray Observatory in Utah. A single proton, a fundamental building block of an atom, slammed into our atmosphere with an energy of 320 electron volts. To put that staggering number in perspective, it was millions of times more powerful than anything we can produce in our largest particle collider. This was not just a cosmic ray. It was a cosmic anomaly, a fundamental challenge written in a subatomic bullet. The true mystery lies not just in its energy, but in its origin. According to our best understanding of physics, no known object within our own Milky Way galaxy possesses a magnetic field strong enough, or is large enough, to act as a particle accelerator of that magnitude. It should be impossible for a galactic source to give a proton that kind of kick. So where did it come from? The leading theory points its finger far beyond our galactic borders, toward the violent hearts of distant active galaxies or colliding galaxy clusters. But this extragalactic journey introduces another profound puzzle, known as the Greisen-Zatsepin-Kuzmin limit. This limit, often called the GZK limit, is a cosmic speed bump. It states that ultra-high energy cosmic rays traveling across the vast intergalactic distances should lose their energy. They do this by colliding with the faint, ancient afterglow of the Big Bang, the cosmic microwave background radiation. Over billions of light years, this constant bombardment should drain a particle's energy, imposing a theoretical ceiling on what can reach Earth from far away. The Oh My God particle, however, smashed right through that ceiling. Its detected energy was far higher than the GZK limit should allow for any particle arriving from a distant galaxy. So we are left with two equally baffling possibilities. Either this particle came from something monstrously powerful and relatively nearby that we have not yet discovered, or our understanding of how particles lose energy across the universe is fundamentally incomplete. One tiny proton has placed our map of cosmic physics in question. That ceiling was shattered again, decades later, by a particle with a name fit for a deity. In May 2021, the Telescope Array project in Utah's high desert recorded a cosmic ray strike of unimaginable force. Its energy was measured at 240 electron volts, placing it firmly in the same league as the legendary Oh My God particle. Scientists, in awe of its power and its arrival from the direction of our own Milky Way's galactic plane, named it Amaterasu, after the Japanese goddess of the sun. The detection itself was a triumph of global collaboration. A network of over 500 scintillator detectors spread across 700 square kilometers of remote Utah wilderness, silently waiting for these rare, catastrophic events. But the data brought not answers, only a deeper, more profound confusion. When researchers traced the incoming path of the Amaterasu particle back to its cosmic origin, Their pointer landed not on a brilliant quasar or a swirling galaxy, but on a vast, seemingly empty void in the local void region, a desolate stretch of space between galactic filaments. It was the equivalent of tracing a cannonball's trajectory back to a source and finding only blank sky. This blank sky origin is what makes Amaterasu so deeply troubling. Our best models for cosmic accelerators all point to extreme, violent environments. We look to the furious jets of active galactic nuclei, the cataclysmic mergers of neutron stars, or the explosive deaths of massive stars as gamma-ray bursts. These are places of chaos, with magnetic fields strong enough to sling particles to near light speed. Yet Amaterasu did not come from any such place we can identify. It came from a cosmic desert. This presents a paradox that shakes astrophysics to its core. Either there is a previously unknown, unimaginably powerful object hidden in that void, something so dark and quiet it escapes all our telescopes, or our understanding of how these particles travel through the magnetized fabric of the universe is fundamentally wrong. Perhaps they can bend in ways we do not predict, making a mockery of our backtracking calculations. The Amaterasu particle is not just a mystery, it is a cosmic rebuke, a sign that the universe holds its most powerful secrets in the emptiest of places. These ultra-rare particles exist at the very edge of what we can measure, but they are not the whole story. To truly understand the cosmic ray mystery, we must step back and look at the entire population, the vast cosmic sea from which these giants emerge. Scientists do this by plotting a graph, a cosmic census of power. On one axis is the energy of each particle. On the other is how frequently they strike us. This graph reveals a shape with a startling, familiar feature. As you move from the lower energy cosmic rays, which arrive by the thousands every second, up toward the rarefied territory of particles like Amaterasu, the line on the graph does something unexpected. It develops a distinct bend, a sharp kink that astrophysicists call, quite simply, the ankle. This is not a single event, but a critical transition point in the very nature of cosmic rays, occurring around 10 to the power of 18.5 electron volts. It is as if the universe itself has drawn a line in the sand. The cosmic rays with energies below the ankle, the ones that make up the vast majority of the shower raining down on Earth, are believed to be born within our own Milky Way galaxy. They are likely accelerated by the shock waves of exploding stars, our local supernova remnants whipping particles to incredible, but still galactic, speeds. But above the ankle, the particles change. Their far higher energies suggest they have undergone a far more violent birth, one that our galaxy simply cannot provide. This is the realm of the extragalactic cosmic rays, the visitors from beyond, like the oh my god particle. So the ankle marks a cosmic border crossing. But what exactly happens at this border? What physical process creates this sharp bend in the graph? That is the profound puzzle. One leading idea is that it marks the point where our galaxy's own magnetic field, which acts like a vast, invisible cage, finally loses its grip. Below the ankle, these magnetic fields can trap and confine the particles, keeping them swirling around the Milky Way for millions of years. But once a particle is accelerated beyond that critical energy threshold, it becomes too powerful, too fast. It punches straight through the galactic magnetic barrier like a bullet through paper and escapes into intergalactic space, only to perhaps find its way to us. Another possibility is that the ankle represents a complete shift in the cosmic accelerators themselves. Perhaps below it, the engines are the relatively gentle shock waves of supernova. Above it, the baton is passed to the true monsters of the cosmos, the jets of supermassive black holes or colliding galaxy clusters. The ankle, then, is a cosmic clue written in statistics. It is the universe telling us that there are two distinct populations of these mysterious particles, governed by different rules and born in different realms. Unlocking why this bend exists is key to mapping the invisible architecture of our universe, from our galactic neighborhood to the violent depths beyond. That cosmic border crossing at the ankle points us toward the extragalactic realm, but it does not give us a map. For decades, scientists hunting for the sources of the most powerful cosmic rays faced a frustrating reality. These particles are electrically charged, which means as they travel across millions of light years, the weak but pervasive magnetic fields that weave through the cosmos gently bend their paths. It is like trying to trace a bullet back to the gun that fired it after it has ricocheted off a dozen invisible walls. The arrival directions on our sky maps appeared utterly random, a uniform sprinkle of mystery. That changed with a monumental discovery from the plains of Argentina. The Pierre Auger Observatory, an array of over 1,600 water tank detectors spread across an area the size of Rhode Island, spent years patiently recording the rare impacts of ultra-high energy cosmic rays. By analyzing the collective data from thousands of these events, a pattern finally began to emerge from the noise. The scientists found a slight but significant statistical excess, a cosmic ray hotspot. More of these ultra-high energy particles than expected were arriving from a broad, fuzzy patch of sky near the constellation Ursa Major, the Great Bear. This was a monumental clue. For the first time, we had a hint of a direction, a general neighborhood in the cosmos where these monstrous particle accelerators might be lurking. It was the first real evidence that the sources of these rays were not evenly distributed across the universe, but clustered. Yet this clue instantly deepened the puzzle. The hotspot is not a pinprick on the map. It is a vast region spanning about 115 degrees of the sky, an area far too large to point to a single galaxy or quasar. Within that enormous swath of space, our telescopes see no obvious, cataclysmic object powerful enough to be the culprit. There are no brilliant active galactic nuclei, no spectacular galaxy collisions screaming for attention in that particular direction. So what are we seeing? The hotspot likely is not a single source, but a smeared-out signature. Imagine standing in a foggy forest, hearing shouts from a distant village. You can tell the general direction the sound is coming from, but the fog blurs the individual houses. The magnetic fields of intergalactic space act as that fog, scattering and bending the paths of these charged particles over their epic journeys. The hotspot, then, could be the blurred glow from a nearby cluster of galaxies, or perhaps from a dense filament of the cosmic web where many galaxies are gathered. The accelerators within that cluster, working together, could be producing the excess of rays we detect. This makes the search both more exciting and more complex. We are not looking for a single cosmic lighthouse, but perhaps an entire city of them, their combined light diffused by magnetic fog. The Auger hotspot is a tantalizing first step. It tells us we are on the right track, that sources are out there and they leave a trace. But it also underscores the immense challenge of cosmic ray astronomy. We are detectives trying to solve a crime where the bullets curve, and the crime scene is billions of light years wide. The search for cosmic ray sources often feels like a modern detective story, but one of the most compelling clues in the casebook comes from over a century ago. On June 30th, 1908, a cataclysm unfolded in the remote skies above Siberia. A blinding fireball tore through the atmosphere, followed by a shock wave so powerful it flattened 80 million trees across 2,000 square kilometers of the Tunguska forest. The explosion, estimated to be hundreds of times more powerful than the atomic bomb dropped on Hiroshima, released enough energy to light up the night skies across Europe and Asia for days. For decades, the leading explanation was the atmospheric explosion of a small comet or stony asteroid. Yet, the complete absence of any impact crater or any significant fragments of an extraterrestrial body has left the door open for a far more exotic and controversial possibility. What if the Tunguska event was not caused by a celestial rock, but by a cosmic ray of unimaginable density? The hypothesis suggests the culprit was not a mountain-sized object, but something microscopic. One version proposes a primordial black hole, a hypothetical relic from the Big Bang itself, no larger than an atom, but with the mass of a mountain. Traveling at near light speed, such an object would have sliced through the Earth like a bullet through smoke, entering the atmosphere over Siberia and exiting out the other side of the planet, transferring its immense kinetic energy into a devastating atmospheric blast along the way. Another speculative candidate is a nugget of strange matter, a theoretical form of ultra-dense material made of strange quarks. A small chunk of this stuff, stable and incredibly heavy, could have behaved similarly, punching through our planet and detonating in the air. The arguments for this cosmic ray theory are seductive. It neatly explains the total lack of a crater and the absence of meteoritic debris. The explosion pattern, with trees flattened radially outward from a central point, but with a few standing, scorched trunks at the very epicenter, could match the unique energy profile of such an exotic object. Yet the arguments against it are equally powerful. No corresponding seismic event was recorded on the opposite side of the globe, where such an object should have exited. Furthermore, the physics of microscopic black holes or strange matter nuggets surviving a journey across the galaxy to hit Earth remains highly speculative, far outside confirmed science. The Tunguska event, therefore, stands as a permanent question mark. It is a historical cataclysm that matches the destructive scale we might expect from an ultra-high energy cosmic ray event, yet it remains tantalizingly out of reach of proof. It forces us to wonder how many other ancient mysteries in Earth's geological and historical record might be signatures of cosmic violence, written not in craters, but in flattened forests and forgotten fires in the sky. While the ankle marks a border to the extragalactic realm, there is another, lower energy bend in the cosmic ray spectrum that holds the key to our own galactic backyard. This feature is known simply as the knee. It occurs at a much more common, but still formidable, energy of around 10 to the power of 15 electron volts. On the graph plotting cosmic ray numbers against their power, this is where the line takes a sharp, steep dive downward. Above the knee, cosmic rays become drastically rarer. This is not a random statistical blip. It is a fundamental limit, a ceiling written into the very fabric of our galaxy. The leading explanation is that the knee represents the maximum energy to which a cosmic ray can be accelerated by the shock waves from supernova explosions within the Milky Way. Think of our galaxy's supernova remnants as immense natural particle accelerators. For thousands of years after a star explodes, its expanding shockwave plows through interstellar space, and the tangled magnetic fields within it can trap charged particles, bouncing them back and forth like ping-pong balls, each time giving them a slight boost in speed. Over centuries, particles can be whipped up to incredible energies, but even these titanic engines have their limits. The size of the shockwave, the strength of the magnetic fields, and the time a particle can spend being accelerated all impose a theoretical maximum. That maximum, scientists believe, is precisely what we see as the knee in the data. It is the signature of our galaxy's most powerful natural accelerators hitting their operational peak. Yet, as with all good cosmic mysteries, the knee is not a simple, clean cut. The enigma deepens when we ask, what exactly is hitting this ceiling? Are they all protons, the lightest particles? Or do heavier atomic nuclei, like helium or iron, bend at different points? This is a critical puzzle. If all cosmic rays, regardless of their composition, show a knee at the same energy, it suggests the acceleration limit is set by the size of the accelerator itself, a property of the shockwave. But if protons, helium, and iron each have their own distinct knees at different energies, it points to a limit set by the magnetic fields. In that scenario, a particle's charge and mass determine how easily it can escape the accelerating shockwave, like different-sized objects being flung from a spinning merry-go-round at different speeds. Unraveling this precise structure of the knee is the key to confirming supernova as the primary factories for all the cosmic rays we see buzzing around our galaxy. It is the forensic evidence we need to close the case. So while the ankle points to monsters beyond our galaxy, the knee is the fingerprint of the local titans, the supernova remnants whose shock waves have been seeding the Milky Way with invisible, high-energy particles for billions of years. The shape of that bend tells the story of their power and their limits. The supernova shock waves that shape the knee are a force of creation within our galaxy, but some of their products may be shaping the destiny of our own planet in a far more intimate way. This brings us to one of the most contentious and profound ideas in modern science, the hypothesis that cosmic rays are directly involved in controlling Earth's climate. The theory, championed by scientists like Henrik Svensmark, proposes a stunning cosmic connection. It suggests that the stream of galactic cosmic rays constantly bathing our atmosphere acts as a subtle dial for global cloud cover, and by extension, the planet's temperature. Here is how it might work. When a high-energy cosmic ray, often just a single proton, slams into the upper atmosphere, it shatters air molecules in a cascading particle shower. This process creates charged particles, or ions. These ions, the theory goes, can act as seeds around which water vapor can condense, forming the tiny aerosol particles necessary for clouds to begin forming, particularly the low-level, fluffy clouds that reflect sunlight back into space. More cosmic rays would mean more ions, potentially more clouds, and a cooler planet. Fewer cosmic rays would mean fewer clouds, allowing more sunlight to reach the surface and warm it. This would link the climate of our world directly to the magnetic mood of our sun and the structure of our galaxy. When the sun is active, its strengthened magnetic field and solar wind buffets away more galactic cosmic rays, reducing their flux at Earth. According to the hypothesis, this should lead to fewer clouds and a warming trend. When the sun is quiet, more cosmic rays get through, seeding more clouds and contributing to cooling. It is an elegant idea that ties together cosmic and terrestrial forces. Evidence for this has been sought in the laboratory. The most famous experiment is called CLOUD, conducted at the CERN Particle Physics Laboratory in Switzerland. Scientists there used a particle beam to simulate cosmic rays inside a pristine atmospheric chamber. Their results have shown that ionization from these rays can, under very specific and controlled conditions, enhance the formation rate of the molecular clusters that can grow into cloud seeds. This proved the first step of the process is physically possible. Yet, This is where the fierce scientific debate ignites. While the initial step is plausible, the critical question is one of scale. Can this ion-induced process compete with, or significantly influence, the many other far more powerful sources of cloud-seeding particles in our atmosphere, like dust, sea spray, or pollution from human activity? Most climate models and large-scale observational studies have so far found the cosmic ray effect on global cloud cover to be very small, perhaps even negligible. The climate system is a chaotic orchestra of countless factors, and isolating the violin of cosmic rays from the roar of greenhouse gases, ocean currents, and natural variability has proven immensely difficult. This is precisely why the idea remains a profound enigma. If it were true, even in a small way, it would mean the weather outside your window is partially orchestrated by exploding stars tens of thousands of light years away, and the magnetic fury of our own sun. It would weave a thread of cause and effect from the heart of the galaxy to the formation of a single raindrop. The controversy is not about the beauty of the connection, but about its real-world strength. Does this cosmic whisper get lost in the terrestrial roar? Or is it a quiet, persistent rhythm in the heartbeat of our planet's climate? The search for a definitive answer continues, making this one of the most fascinating borderlands between astrophysics and Earth science. Our planet's climate may feel the subtle touch of cosmic rays, but these particles can also carry signatures of something far more exotic. Among the steady rain of protons and atomic nuclei, instruments have detected a puzzling surplus of antimatter. Specifically, an overabundance of positrons, the antimatter twins of electrons. This is the cosmic positron excess, a mystery measured with exquisite precision by a remarkable instrument attached to the International Space Station. The Alpha Magnetic Spectrometer, a $2 billion cosmic ray detector, has been silently collecting data in the vacuum of space since 2011. Its measurements confirmed something startling. While some positrons are naturally created when regular cosmic rays collide with interstellar gas, the number of high-energy positrons streaming in is far greater than these ordinary processes can explain. The curve on the graph rises where it should fall. It is as if you opened a bag of mixed candy, expecting a few red ones, but found a torrent of them pouring out. This anomaly is not a fluke. It is a persistent signal pointing to a hidden source of antimatter within our galaxy. The hunt for that source has led scientists down two thrilling and profoundly different paths. The first path leads to the spinning corpses of dead stars. Pulsars are incredibly dense neutron stars that whip around like cosmic lighthouses, emitting powerful beams of radiation. Their intense magnetic fields and rapid rotation can accelerate particles and create pairs of electrons and positrons in their violent surroundings. These antimatter particles could then escape into the galaxy, contributing to the excess we see. Several nearby pulsars, like Geminga in the constellation Gemini, are prime suspects. They are powerful enough and located in the right part of the sky to potentially account for the signal. This explanation is compelling because it relies on known, albeit extreme, astrophysics. The second path, however, ventures into the realm of the completely unknown. It points to dark matter, the invisible substance that makes up most of the mass of the universe. Some theories suggest that dark matter particles are their own antimatter counterparts. If two of these particles were to collide, they could annihilate each other in a flash of pure energy, producing a shower of standard particles, including pairs of electrons and positrons. The observed positron excess, particularly its specific shape across different energies, could be the first indirect fingerprint of dark matter annihilating in the halo of our Milky Way. This possibility sends a jolt of excitement through the physics community, as it would be our first tangible clue to the nature of this cosmic ghost. So we are left with a beautiful high-stakes puzzle. Is the positron excess the relatively ordinary, if spectacular, fallout from nearby stellar corpses? Or is it the extraordinary whisper of the universe's dominant, unseen matter revealing itself through annihilation? The alpha magnetic spectrometer continues its watch, gathering more data to refine the shape of the positron curve. Each new data point is a vote for one cosmic story over the other, a slow and meticulous process of listening to what the antimatter from the void is trying to tell us. Antimatter's story in cosmic rays grows even stranger. Alongside the puzzling flood of positrons, detectors have recorded another unexpected surplus, this time of antiprotons. These are not just the opposites of electrons, but the mirror images of protons themselves, the very building blocks of ordinary matter. According to our standard models of how cosmic rays travel and interact through the galaxy, the number of these antiprotons should be relatively low. They are secondary products, created only when high-energy protons, the primary cosmic rays, smash into the thin gas between the stars. These violent collisions can spawn pairs of protons and antiprotons, but the math has consistently fallen short. The observed flux is higher, a steady, undeniable excess that mirrors the positron puzzle. This antiproton surplus forces us to re-examine the cosmic ray life cycle. One compelling possibility is that our models of the galactic medium are simply incomplete. Perhaps the interstellar gas is denser in certain regions, or the magnetic fields that confine cosmic rays are more complex, leading to more frequent proton collisions and thus more antiproton production than we calculated. Supernova remnants, those galactic accelerators, might be even more efficient at both creating and trapping these secondary antiparticles than we thought. It is a reminder that our own Milky Way, which we map with light, might have a hidden topography of matter and magnetic fields visible only through these rare particle signatures. Yet, just like with the positrons, the shadow of dark matter looms over this mystery. If dark matter particles are indeed their own antimatter counterparts, their annihilations would not only produce electrons and positrons, but also quarks and gluons that would rapidly coalesce into protons and antiprotons. The energy spectrum of the observed antiproton excess, its particular distribution across different energy levels, could be the unique calling card of such annihilations. Scientists pore over this spectral shape with intense scrutiny because it holds the power to discriminate. The fingerprint from dark matter annihilation would look different from the fingerprint left by mundane astrophysical processes like proton collisions in gas clouds. This makes the antiproton surplus a critical piece in a much larger puzzle. It is not an isolated anomaly, but a parallel clue to the positron excess. Together, they form a two-pronged test for any theory of dark matter. A proposed dark matter particle must explain both signals simultaneously, their relative amounts and their precise energy spectra. It is a cosmic lock that requires two keys to open. Each new measurement of these antimatter particles, from space-based detectors and balloon-borne experiments, tightens the constraints, narrowing down the possible properties of the universe's most elusive substance. So every antiproton that reaches our detectors is more than a curiosity. It is a potential messenger from the dark sector, carrying encrypted details about the true nature of most of the matter in the cosmos. The search for dark matter's signature is a patient, statistical game. But the universe also produces bursts of violence so intense they can be seen from the far edge of the cosmos. Gamma-ray bursts are the single brightest electromagnetic events known. Flashes of light so powerful they outshine entire galaxies for a few fleeting seconds. In that apocalyptic fury, some scientists believe, lies the birthplace of the most extreme cosmic rays. The hypothesis is compelling in its sheer scale. A gamma-ray burst represents the catastrophic collapse of a massive star or the merger of two ultra-dense neutron stars. These events unleash relativistic jets, focused beams of energy and particles screaming into space at over 99.9% the speed of light. Within these jets, turbulent magnetic fields could act as nature's ultimate particle accelerator, taking protons or atomic nuclei and slinging them to energies that dwarf even our supernova. If this is true, then a significant fraction of the ultra-high energy cosmic rays that baffle us, particles like Amaterasu, could be the long-lived shrapnel from these brief cosmic detonations. This brings our detective story to a specific patch of sky, the Vela region. Named for the Vela constellation, this area is notorious in astrophysics. It contains the Vela supernova remnant, a local cosmic landmark, but more importantly, it is a direction from which multiple gamma-ray bursts have been detected over the years. It is a known factory of these monstrous explosions. The tantalizing question is whether the cosmic rays we detect on Earth show a statistical excess arriving from that same direction. Can we connect the dots between a fleeting flash of gamma rays, seen perhaps billions of years ago, and a single particle arriving today? The challenge here is almost incomprehensibly difficult. A gamma-ray burst is over in moments, its light traveling to us in a straight line. A cosmic ray, however, is a charged particle. As we have seen, it does not travel in a straight line. It is buffeted and curved by galactic and intergalactic magnetic fields throughout its multimillion or billion-year journey. By the time it finally reaches us, its original direction is completely scrambled. It is like trying to match a specific gust of wind in your backyard today to a particular volcano that erupted on another continent a century ago. The wind has mixed with global weather patterns, losing all trace of its origin. Furthermore, the timing is utterly disconnected. The gamma-ray burst we see in our telescopes happened in the distant past. The cosmic ray it might have produced would have begun its journey at the same moment, but its path was so long and tortuous that it is only arriving now, eons later. There is no simultaneous signal to correlate. The only possible link is a statistical one. If we see more ultra-high energy cosmic rays coming from the general direction of a known gamma-ray burst hotspot, like Vela, than from other, quieter parts of the sky, it would be a crucial clue. It would suggest that region of space is particularly proficient at generating these extreme particles, and gamma-ray bursts are the prime candidate for the job. So far, the evidence remains murky. The data is sparse, and the magnetic scrambling is severe. The connection remains a powerful hypothesis, a story of cosmic cause and effect written across unimaginable distances and timescales. It forces us to see a gamma-ray burst not just as a brilliant flash, but as a silent gunshot, whose bullet might only find its target, our atmosphere, millions of years after the trigger was pulled. Deep in the heart of our own galaxy, a different kind of glow holds a secret. The center of the Milky Way is a crowded, violent place, home to a supermassive black hole and millions of densely packed stars. For years, the Fermi Gamma Ray Space Telescope has mapped this region in high-energy light. expecting to see gamma rays from known sources like pulsars and gas clouds. But the data revealed something more: a diffuse and puzzling halo of excess gamma ray emission that extends thousands of light years from the galactic core. It is too much, and it is in the wrong place. This is the Galactic Center excess. The key to the mystery lies in how gamma rays are made there. Ordinary processes are well understood. When cosmic rays, those high-energy protons and electrons accelerated by supernova, collide with the clouds of cold gas that fill the galactic center, they produce pions, particles that rapidly decay into gamma rays. This should create a predictable, smooth glow. Yet Fermi's maps show an additional, spherical haze of gamma rays that cannot be explained by these standard cosmic ray interactions alone. It is as if you calculated the light from every known street lamp in a city, only to find the entire downtown bathed in an unexplained, uniform twilight. This excess glow has made the Galactic Center one of the most promising hunting grounds for indirect dark matter detection. The theory is elegant. Imagine dark matter particles drawn by gravity into a vast, diffuse cloud at the galaxy's heart. If these particles are their own antimatter, as many theories suggest, they could occasionally collide and annihilate. That annihilation would produce a cascade of standard particles, which would then decay into gamma rays with a very specific energy signature. Crucially, because dark matter is believed to form a smooth, spherical halo around the galaxy, its annihilation signal would look just like what Fermi sees: a round, symmetric excess of light, not clumped around any particular star or gas cloud. The energy spectrum of the excess, the specific brightness at different gamma ray energies, even seems to match predictions for certain proposed dark matter particles. But as with all great cosmic clues, alternative explanations have emerged. One points to a hidden population of ancient, faint pulsars. Thousands of these spinning neutron stars, too dim for us to see individually, could be clustered in the galactic center. Each one would produce gamma rays, and their combined diffuse glow could mimic a smooth excess. It is the difference between seeing a single, bright lighthouse and seeing the combined glow of 1,000 distant candles, their individual flames blurred into a single haze. Another possibility involves a past burst of star formation, a frenzy of stellar births and deaths that occurred millions of years ago, leaving behind a legacy of cosmic rays that are still interacting with gas. The debate is intense because the stakes are cosmic. Is the Galactic Center excess the first clear glimpse of the universe's dominant matter, revealing itself through annihilation? Or is it simply a testament to the chaotic, crowded stellar metropolis at our galaxy's core, a place we are still learning to understand? Each new analysis of Fermi's data sharpens the question, bringing us closer to an answer that could redefine our place in the shadowy architecture of the Milky Way. That theoretical ceiling, the GZK limit, is more than just a speed bump for cosmic rays. It is a cosmic horizon, a fundamental barrier imposed by the very structure of our universe. Named for the three physicists who predicted it in the 1960s, the Greisen-Zatsepin-Kuzmin limit describes a simple, brutal fact of intergalactic travel for the most energetic particles. The space between galaxies is not completely empty. It is filled with the faint, cold glow of the cosmic microwave background, the ancient afterglow of the Big Bang. For an ultra-high energy cosmic ray, a proton traveling at near light speed, this gentle bath of photons is not a harmless glow. It is a dense fog of high-speed bullets. When such a proton collides with one of these background photons, it can produce new particles, most notably a pion. This process steals a tremendous amount of energy from the original cosmic ray. Over a distance of about 150 million light-years, this constant drain should sap the energy of any proton above a certain threshold, roughly 10 to the power of 20 electron volts. This creates a sharp cutoff in the cosmic ray spectrum, an absolute horizon beyond which we should see nothing. It is a fundamental prediction of well-tested physics, combining Einstein's special relativity with our understanding of particle interactions. The universe, according to this rule, should be opaque to the most extreme cosmic rays from distant sources. They simply cannot make the long journey to Earth without being crippled by the cosmic fog. This is where the mystery punches through. Particles like the Oh My God particle and Amaterasu possess energies far, far above the GZK cutoff. They have arrived with a power that, according to the limit, they should have lost billions of years ago. It is as if a marathon runner showed up at the finish line not only unexhausted, but moving faster than when they started. Their very existence presents us with two equally staggering possibilities, each rewriting a different chapter of our cosmic understanding. The first possibility is one of proximity. Perhaps these ultra-high energy cosmic rays are not intergalactic travelers at all, but local phenomena. If their source is within our own galactic neighborhood, within a mere 100 to 200 million light-years, then they would not have had enough time or distance to interact significantly with the cosmic microwave background. They would have slipped under the GZK horizon. This forces a profound question. What unimaginable object, relatively close by in cosmic terms, is capable of launching such projectiles? We have already ruled out the known engines within our own Milky Way, so we must be looking for a hidden monster in our intergalactic backyard, a nearby active galaxy, or a colossal cosmic event we have somehow overlooked. The alternative is far more radical. Perhaps our understanding of particle physics at these insane, otherwise unreachable energies is incomplete. The GZK limit relies on our standard model of particle physics, a framework brilliantly confirmed by experiments like the Large Hadron Collider. But the collider operates at energies trillions of times lower than the Oh My God particle. What if, at these extreme frontiers, the rules change? Could protons interact with the cosmic microwave background in a different, less draining way? Or could there be entirely new, unknown particles that are immune to this energy loss, arriving here intact to create the showers we detect? This is the true weight of the GZK horizon mystery. It is not just a puzzle about where cosmic rays come from. It is a direct experimental test of our most fundamental physics in an energy regime we can never hope to recreate in a laboratory. Every ultra-high energy cosmic ray that crashes through the predicted cutoff is a message from the universe, asking us a simple, terrifying question. Is our map of the nearby cosmos missing a titan, or is our map of reality itself incomplete? The Amaterasu particle's origin points to a cosmic address of profound emptiness. Its trajectory leads back not to a brilliant galaxy, but to a region known as the Boots Void. This is not just any empty patch of sky. It is one of the largest known structures in the entire universe, a spherical chasm of near nothingness spanning an almost incomprehensible 330 million light-years across. To grasp that scale, if you placed our Milky Way galaxy inside it, you would have to travel for hundreds of millions of years at the speed of light to reach the other side, encountering almost nothing along the way. It is a true desert on a cosmic scale, containing only a handful of isolated galaxies where our models predict there should be thousands. This is the core of the mystery. Our entire understanding of ultra-high energy cosmic rays is built on the need for monstrous accelerators, environments of extreme violence and power. We look to the hearts of active galaxies, the collisions of galaxy clusters, or the remnants of stellar explosions. The Boots void, by its very definition, has none of these things. It is a place where the cosmic web, the large-scale structure of the universe, has thinned out to almost nothing. So how can the most energetic particle we have ever recorded come from a place that has, seemingly, nothing to offer? Scientists are grappling with two broad, equally mind-bending possibilities. The first involves a cosmic illusion. Perhaps the particle did not originate in the void at all. The magnetic fields that permeate the space between galaxies are weak, but over distances of billions of light years, they can act like a complex lens, gently bending the path of a charged particle. It is possible that Amaterasu was born in a spectacular event far beyond the Boots void, in a distant, crowded cluster of galaxies. Its path could have been curved and focused by these intergalactic fields in such a way that, when we trace its final approach back in a straight line, it appears to come from the void. The void, in this case, is merely a blind spot in our cosmic vision, a place where the true source is hidden behind a curtain of magnetic fog. The second possibility is far more radical. What if the Boots void is not empty of process? What if the vast, quiet spaces between the filaments of the cosmic web are themselves sites of unknown physics? Some speculative theories suggest that such immense voids could be where cosmic strings, hypothetical defects in the fabric of spacetime from the universe's first moments, might reside. The immense energy stored in such a string could, in theory, be tapped to accelerate particles. Others wonder if dark matter, which likely fills the void even if galaxies do not, could somehow annihilate or decay in a way that produces these ultra-rare bullets. This would mean the emptiness is an illusion of light, not of matter or potential. The Boots void origin story forces us to confront the limits of our maps. We chart the universe with telescopes that see stars and galaxies, but the cosmos is built of both light and shadow. The Amaterasu particle is a messenger from the shadow, insisting that the great voids are not merely blanks on our charts, but regions that might hold their own quiet and terrifying secrets. It suggests that sometimes the most powerful answers come not from the brightest places, but from the darkest, emptiest corners of existence. The energies we are discussing are not just astronomical, they are humbling. To grasp the raw power packed into a single ultra-high energy cosmic ray, we need to compare it to the pinnacle of our own technological achievement, the Large Hadron Collider. Buried beneath the Swiss-French border, this 17-mile ring of superconducting magnets is humanity's most powerful microscope, accelerating protons to energies of 6.5 tera-electron volts. It is a triumph of engineering, capable of recreating conditions a fraction of a second after the Big Bang. Yet, a single particle like the Oh My God particle arrived with an energy of 320 electron volts. That is not just a little more. It is millions of times more energy than we can impart to a proton in our greatest machine. Nature, it seems, operates a particle accelerator in the sky that utterly dwarfs anything we can build. This is the core of the enigma we call the LHC in the sky phenomenon. What cosmic mechanism is so incomprehensibly powerful that it can take a single subatomic speck and launch it with the force of a professionally thrown baseball? The search for this natural engine leads us to the most violent precincts of the universe. Our prime suspect is the relativistic jet screaming from an active galactic nucleus. At the heart of many galaxies, including our own, sits a supermassive black hole. When such a monster feeds voraciously on surrounding gas and stars, it does not swallow all the material. Some gets channeled by unimaginably strong magnetic fields into a pair of narrow, opposing beams that blast out at nearly the speed of light. Within these jets, turbulent magnetic shocks could act like a series of accelerating rings, far larger and more powerful than the LHC, bouncing particles back and forth across vast distances until they reach these insane energies. Another colossal candidate is the shockwave from colliding galaxy clusters. When two of these largest gravitationally bound structures in the universe smash together over billions of years, they do not just mix stars. They create titanic tsunamis of hot gas and magnetic fury moving at thousands of kilometers per second. A particle caught in the front of this merging shock could be swept up and accelerated across millions of light years, gaining a little more speed with each pass. The sheer scale of these engines is the key. Where our Large Hadron Collider is 17 miles across, these cosmic accelerators are tens of thousands of light years long. They have millions of years to operate, not microseconds. And their power source is not the electrical grid of a continent, but the gravitational free fall of matter into a black hole with the mass of billions of suns, or the kinetic energy of entire galaxies in collision. This comparison forces a profound shift in perspective. We often think of our technology as advanced, but in the face of such cosmic engineering, it is primitive. We are like Stone Age builders looking at a skyscraper, trying to understand how it stands. Every ultra-high energy cosmic ray that strikes our atmosphere is a piece of shrapnel from a cosmic explosion so vast. Its accelerator makes our grandest invention look like a child's toy. The mystery is not just where they come from, but how the universe routinely performs feats of particle acceleration we can barely dream of replicating. The universe's most violent particle accelerators may have played a quiet, foundational role in the story of life itself. This is one of the most profound and speculative connections in all of science, a bridge between the cataclysmic and the delicate. The theory suggests that the constant rain of cosmic rays onto the early Earth was not just a background hazard, but an essential spark. 4 billion years ago, our planet was a very different place, with a primitive atmosphere rich in gases like methane, ammonia, and water vapor, and oceans covering a turbulent volcanic surface. In this primordial soup, the building blocks of life, amino acids and nucleobases, needed to form from simpler chemicals. The question has always been, where did the energy come from to drive these complex reactions? Lightning and volcanic heat are the usual suspects, but there is another, more constant source that blanketed the entire planet: cosmic rays. When a high-energy cosmic ray, or more commonly the secondary particles it creates in the atmosphere, strikes a molecule of water or methane, it can rip electrons away, creating a highly reactive ion. This ion can then trigger a cascade of chemical reactions, shuffling atoms into new and more complex arrangements. In the dense, chemical-rich environment of the early atmosphere, or in subsurface water pockets warmed by geothermal heat, this constant planet-wide irradiation could have acted as a slow, persistent cook, gradually brewing the organic ingredients for life. Laboratory experiments have tested this idea with striking results. Scientists have recreated the presumed mix of gases in the early Earth's atmosphere in sealed chambers, and then exposed them to sources of ionizing radiation that mimic cosmic rays, such as proton beams or gamma rays. In these experiments, they consistently observe the formation of amino acids, the very Lego blocks of proteins, and other complex organic compounds. It is a powerful demonstration that the basic chemistry of life can be jump-started by the same violent processes that create ultra-high energy particles in deep space. The enigma here is one of scale and contribution. No one claims cosmic rays were the sole ingredient, but rather a potential facilitator, one part of a planetary recipe that included sunlight, lightning, and hydrothermal vents. The mystery lies in quantifying their precise role. Could their unique ability to penetrate deep into the atmosphere and even into the upper layers of the ocean or crust have made them especially important in environments where other energy sources were weak? Did they provide a steady, global background of chemical activation that allowed life's precursors to form in shadowy places as well as sunlit ones? This transforms our view of cosmic rays from mere astronomical curiosities or threats into potential cosmic gardeners. Their relentless bombardment, a phenomenon born from stellar explosions and galactic shocks, might have gently stirred the pot of prebiotic chemistry for eons. It suggests a breathtaking continuity, that the same forces that tear stars apart in distant galaxies could also have provided the subtle, persistent nudge that allowed the first self-replicating molecules to coalesce right here. The link remains speculative, a tantalizing thread in the vast tapestry of abiogenesis, but it forces a humbling and beautiful thought that the story of every living thing on Earth may have begun, in part, with a silent rain of bullets from the void. That cosmic rain that may have seeded life arrives from all directions with a strange uniformity. This brings us to a profound mystery not of extreme power, but of puzzling distribution, the anisotropy puzzle at lower energies. Anisotropy simply means directionality, that something comes more from one place than another. For the highest energy cosmic rays, like those from the Auger hotspot, we see hints of this, faint smears on the map pointing back to possible sources. But when we look at the far more common, lower energy cosmic rays that fill our galaxy, the picture is utterly different. They appear to be perfectly isotropic, arriving with equal intensity from every point in the sky. This, on its face, makes no sense. Our solar system is not at the center of the Milky Way. We orbit about halfway out on one of its spiral arms. If cosmic rays are born in sources like supernova remnants scattered unevenly across the galactic disk, we should see a glaring anisotropy. We should see more cosmic rays coming from the direction of the crowded Galactic Center, and fewer from the sparse outer regions and the emptiness beyond the galactic plane. It would be like standing in a forest at night, surrounded by campfires. You would see more light coming from the direction with the densest cluster of fires, not an equal glow from every single direction. Yet our detectors report that equal glow. So why does the cosmic ray sky look the same in every direction? The answer lies in an invisible, cosmic mixing machine, the galactic magnetic field. Our galaxy is threaded through with a weak but immensely complex web of magnetic fields, generated by the motion of charged particles and stellar winds. These fields are not straight lines, but turbulent, twisted, and tangled, filling the space between the stars. For a cosmic ray, a charged particle hurtling through space, this magnetic web is a labyrinth. The moment a proton or atomic nucleus is blasted out from its source, a supernova remnant for instance, it does not fly in a straight line toward us. Instead, it immediately gets caught in this magnetic maze. The field lines act like invisible rails, forcing the particle to spiral around them. With each interaction and deflection, the particle's original direction is lost. Over thousands or millions of years, these cosmic rays bounce and scatter randomly through the galaxy, their paths scrambled beyond recognition. By the time they finally wander into our solar system, they have forgotten where they came from. They have been so thoroughly mixed by the galactic magnetic field that they appear to be coming from a uniform, featureless shell around us. This magnetic mixing explains the isotropy, but it also creates a major challenge for astronomers. It means that for the vast majority of cosmic rays, we cannot simply point a telescope back along their path to find their source. The magnetic field has erased their return address. The only way to uncover their origins is through indirect forensic science, by studying their composition and energy, and matching it to what we think different accelerators, like supernova, should produce. The isotropic sky is therefore a cosmic illusion, a testament not to the uniformity of sources, but to the powerful, invisible hand of the galaxy's magnetic field, patiently stirring its high-energy soup until all directions look the same. The galactic magnetic field may hide the origins of most cosmic rays, but for the highest energy ones born within our own galaxy, there is a specific and elusive quarry. These are the pevitrons, the cosmic engines we believe are responsible for accelerating particles to at least 1 peta-electronvolt, the energy of the galactic need. The name itself is a target, combining peta-electronvolt with the suffix from particle accelerators like the Large Hadron Collider. Finding a pevitron would be the smoking gun, the definitive proof that a specific object in our sky can push protons to the absolute limit our galaxy allows. The hunt is on, and it relies on a clever bit of cosmic detective work. Since we cannot trace charged cosmic rays directly back to their source, we look for the unique calling cards they leave behind. When a proton accelerated to PV energies finally collides with a cloud of interstellar gas near its source, something spectacular happens. That collision produces not just gamma rays, but also subatomic particles called neutrinos. These are the two key signatures: a source glowing with very high-energy gamma rays, and especially one also emitting high-energy neutrinos, is almost certainly a cosmic ray factory, a pevitron in action. Our telescopes have turned these predictions into a sky-wide search. In gamma rays, one of the most promising suspects is a supernova remnant called RxJ 1713.7-3946. This beautiful, expanding shell of debris, the aftermath of a star that exploded about 1,000 years ago, shines brilliantly in very high-energy gamma light. The maps from telescopes like HESS in Namibia show its intricate, filamentary structure glowing like a cosmic ghost. The intense gamma radiation is a strong hint that this remnant is indeed accelerating particles to tremendous speeds. But here lies the core of the pevitron enigma. That brilliant gamma ray glow alone is not conclusive proof. There is a critical ambiguity. Gamma rays can be produced in two ways. The first way is the one we are hoping for, the hadronic process. This is when a proton, accelerated by the remnant's shockwave, smashes into a gas proton, creating a shower of particles that decay into gamma rays. This would confirm the remnant is a proton accelerator, a true pevitron. The second way is the leptonic process. This is when high-energy electrons, also accelerated by the shock, wiggle through magnetic fields and emit gamma rays directly. This process does not require protons at all, so the brilliant glow of RxJ 1713 could just be from electrons, not the protons we are desperate to find. To break this deadlock, we need the other signature, the neutrino. Neutrinos are the ultimate witnesses. They are only produced in hadronic interactions, when protons collide. A single high-energy neutrino detected from the direction of this supernova remnant would be the definitive evidence, the fingerprint of a proton at PV energies. It would confirm beyond doubt that we have found one of the galaxy's long-sought power plants. Yet, despite decades of searching with increasingly sensitive detectors buried in Antarctic ice and under the Mediterranean Sea, that conclusive neutrino signal from a specific galactic pevatron remains elusive. This is why pevatrons are ghostly engines. We see their likely handiwork in the gamma-ray sky. We understand the physics that demands they exist to explain the knee in the cosmic ray spectrum. And we have perfect candidates like RxJ 1713. But the final piece of evidence, the neutrino bullet from a proton gun, has not yet been matched to a specific source. They are the cosmic equivalents of a criminal whose modus operandi we know perfectly, but whose face we have never clearly seen. The hunt continues, a meticulous process of matching gamma-ray maps with neutrino events, slowly tightening the net around the engines that have been seeding our galaxy with high-energy particles for billions of years. The hunt for pevatrons reveals how cosmic rays are both destroyers and creators. This brings us to a process where cosmic violence forges the very elements around us, a phenomenon called spallation. The name itself sounds violent, and it is. As high-energy cosmic rays, mostly protons and alpha particles, rocket through the interstellar medium, they do not always miss their targets. They frequently slam directly into the nuclei of heavier atoms drifting in space, like carbon, nitrogen, or oxygen. These collisions are catastrophic. They blast the target nucleus apart, fragmenting it into smaller, lighter pieces. It is the subatomic equivalent of hitting a ceramic vase with a sledgehammer, the shards flying everywhere. Those shards are new atomic nuclei, and among the most common fragments are the light elements lithium, beryllium, and boron. Here, cosmic rays solve a long-standing cosmic mystery. In the grand furnace of the Big Bang and the nuclear fires of stars, these three light elements are notoriously hard to make. The Big Bang produced vast amounts of hydrogen and helium, but only trace amounts of lithium. Stars, meanwhile, tend to fuse light elements into heavier ones, burning up lithium rather than creating much of it. So for decades, astronomers puzzled over where all the lithium, beryllium, and boron in our galaxy came from. Spallation provided the elegant answer. Cosmic rays are the galactic recyclers, taking the heavier elements cooked in stars and smashing them to produce these lighter ones. This process has been slowly seeding the interstellar gas with lithium for billions of years. Every atom of lithium in your smartphone battery likely owes its existence to a cosmic ray collision that occurred long before our solar system was born. Yet, as with all good cosmic stories, this solution creates a new and precise puzzle. When scientists run the numbers, modeling the observed flux of cosmic rays and their interactions with interstellar gas, they find a persistent discrepancy. The calculations consistently produce less lithium-7, the most common stable isotope of lithium, than we actually observe in the oldest stars and in the general galactic environment. The cosmic ray spallation process seems to be falling short. It is as if a factory's production records show it made 1,000 units, but the warehouse inventory shows 1,200. Something is off. This lithium deficit points to a gap in our understanding. Perhaps the cosmic ray flux in the distant past, when these old stars were forming, was significantly higher than it is today. More cosmic rays would mean more spallation, producing the extra lithium we see frozen into those ancient stellar atmospheres. Alternatively, our models of the galactic chemical evolution, the intricate dance of star formation, supernova explosions, and gas mixing might be missing a key step. Could there be other unknown sources of lithium, perhaps from certain types of supernova or from the winds of evolved stars? Or more intriguingly, could there be an entirely different class of lower energy cosmic rays, a population we do not fully account for, that is particularly efficient at making lithium through spallation? This tiny discrepancy in the abundance of a single element is a forensic clue. It suggests our census of the galaxy's particle population, and its history is incomplete. The very process that explains the existence of a fundamental element is now hinting that the cosmic ray story has hidden chapters, waiting to be read in the faint light of ancient stars. While cosmic rays forge elements in the depths of space, their journey ends in a spectacular burst of creation high above our heads. When a primary cosmic ray, often a single proton, strikes the nucleus of an atom in the upper atmosphere, it does not simply bounce off. It explodes. This collision triggers a cascading avalanche, a particle shower that rains down toward the surface. Among the myriad particles born in this violent genesis are muons. Think of them as the heavy, unstable cousins of electrons, packing over 200 times the mass but sharing the same electric charge. They are created in abundance, and for decades, their numbers have been meticulously counted by detectors buried deep underground, shielded from lesser radiation. These counts, however, have revealed a stubborn and significant discrepancy. The measured ratio of muons to other particles in these cosmic ray showers consistently exceeds the predictions of our most sophisticated computer simulations. It is as if every time a recipe calls for 1 cup of flour, the baker finds 1¼ cups in the bowl, without explanation. This muon surplus is not a minor accounting error. It is a direct challenge to our understanding of how matter behaves at energies far beyond our terrestrial laboratories. The simulations are built upon the bedrock of the Standard Model of Particle Physics, our well-tested rulebook for the subatomic world. They model the intricate chain reaction of a cosmic ray air shower with immense precision, factoring in how quarks and gluons interact during those first catastrophic collisions. Yet the real world, measured in mines and tunnels beneath mountains, keeps producing more muons than the rulebook says it should. This anomaly points to 2 profound possibilities. The first is that our models of these high-energy particle interactions, while excellent, are subtly incomplete. Perhaps the way energy is shared among the particles in the first moments of the shower is slightly different than we calculate, leading to a more prolific production of the particles that decay into muons. The second possibility is far more exciting. It could be a faint hint of physics beyond the Standard Model. What if the cascade involves the brief existence of an unknown particle, or a new type of interaction that favors the creation of muons? This would be a crack in the foundational wall of modern physics, glimpsed not in a multibillion-dollar collider, but in the free, natural experiments conducted by the cosmos above us. This is why scientists operate delicate detectors in places like the Gran Sasso Laboratory in Italy, buried under a mountain of rock. They are listening to the rain of muons, these fleeting cosmic messengers, trying to decode the persistent excess in their numbers. Each muon that penetrates deep into the Earth carries with it a tiny, encrypted message about the first instance of a cosmic ray's death, and the true laws governing matter at its most violent. Solving this anomaly would not just fix a simulation, it could rewrite a chapter in the fundamental story of our universe. The muon surplus hints at physics we do not yet grasp, but some cosmic ray events defy explanation entirely. High in the Bolivian Andes in the 1970s, Detectors at the Chakotay Observatory recorded something that should not exist. They captured the aftermath of cosmic ray strikes that produced air showers with a bizarre, almost inverted composition. These were named Centauro events, after the mythical half-man, half-horse creature, because they seemed to be a hybrid of two different realities. In a normal cosmic ray shower, when a proton hits the atmosphere, it creates a balanced mix of particles. You get a cascade of electrons, photons, and muons, alongside some hadrons, which are particles like protons and neutrons that feel the strong nuclear force. The Centauro events shattered this expectation. They produced an overwhelming flood of hadrons, dozens or even hundreds of them, while generating almost no electrons or photons at all. It was as if a standard firework had been replaced by one that produced only the loud bangs and none of the sparkling light. This imbalance points to a radically different kind of primary particle entering our atmosphere, something that interacts not through the familiar electromagnetic force, but through some exotic process that favors the strong force. For decades, these events were considered anomalies, perhaps even artifacts of the early detectors, but they refused to go away. Modern experiments like the Pierre Auger Observatory have continued to search for them, refining the criteria and scanning the skies. While classic Centauro events remain extremely rare, the hunt has revealed other exotic shower types with similar strange imbalances, suggesting the phenomenon is real and profoundly puzzling. So what could possibly create such a lopsided explosion in the sky? One leading hypothesis points to a state of matter that exists only in theory, strange quark matter. This is a super-dense, stable substance theorized to be made of roughly equal numbers of up, down, and strange quarks. A small nugget of this material, called a strangelet, could be traveling through space. If it struck our atmosphere, it would not shatter like a normal atomic nucleus. Instead, it would interact via the strong force almost immediately, dumping its immense energy directly into a torrent of hadrons without the usual electromagnetic cascade. It would be a bullet made of pure nuclear force. Another possibility is the creation of a theoretical particle called a disoriented chiral condensate, a bizarre, temporary bubble of space where the rules governing quarks are fundamentally altered, leading to an explosive burst of protons and neutrons. The profound mystery of the Centauro events is that they represent a form of particle physics we cannot recreate. Our largest colliders smash particles together at incredible energies, but they have never produced an event that looks like this. The universe, it seems, is conducting experiments in high-energy physics that we can only witness by chance, when a fragment of its most exotic material happens to fall on our planet. Each potential detection is a message written in hadrons, suggesting that the building blocks of reality might assemble themselves in ways we have never dared to imagine, and that these strange assemblies are, at this very moment, silently raining down upon us. The sun's own magnetic heartbeat creates a protective rhythm for our planet. Every 11 years, our star cycles through periods of intense activity and relative calm, a pattern marked by the rise and fall of sunspots on its surface. This solar cycle is not just a light show, it directly governs the flood of galactic cosmic rays that washes over Earth. When the sun is at its maximum, bristling with solar flares and coronal mass ejections, its magnetic field grows stronger and more complex. The solar wind, that constant stream of charged particles flowing from the sun, becomes a raging torrent. This swollen heliosphere, the vast magnetic bubble the sun blows into interstellar space, acts as a powerful shield. It deflects and scatters the lower energy galactic cosmic rays, preventing them from penetrating deep into the inner solar system. The result is a measurable dip in cosmic ray intensity at Earth, a lull in the invisible rain. When solar activity wanes at the cycle's minimum, that magnetic shield weakens. The heliosphere shrinks and grows quieter, and the dam breaks. Galactic cosmic rays, unimpeded, surge inward, and our detectors record a significant rise in their flux. This solar modulation is a beautifully predictable dance, a cosmic tug of war between the sun's magnetic fury and the relentless pressure from the galaxy. Yet, for all its apparent regularity, modeling this dance with perfect precision has proven to be a stubborn mystery. Scientists create intricate computer simulations, factoring in the sun's tilted magnetic field, the turbulent flow of the solar wind, and the diffusion of particles through magnetic turbulence. But time and again, the predictions diverge from the actual measurements. The observed modulation is often stronger or weaker than the model's forecast, and the timing of the peaks and valleys can be subtly off. These discrepancies are more than academic curiosities. They are critical warnings. Our entire strategy for protecting astronauts on journeys to the Moon or Mars relies on accurately forecasting this cosmic ray flux. A long-duration mission planned during a predicted solar maximum, counting on a natural reduction in galactic radiation, could be catastrophically mistimed if our models are wrong. Similarly, satellites and spacecraft electronics are hardened against radiation based on these predictions. An unexpected surge of particles during a supposedly quiet period could fry sensitive circuits, crippling communication networks or navigation systems. The fact that our models keep missing the mark points to fundamental gaps in our understanding of the heliosphere's true structure. Is the boundary where the solar wind meets interstellar space more porous or dynamic than we think? Are there hidden currents or magnetic structures within the bubble that channel particles in unexpected ways? Each errant prediction is a clue that the sun's protective shield is far more complex than a simple, smooth bubble. It is a chaotic, living membrane, and until we can chart its every ripple and fold, those who venture beyond Earth's atmosphere will be navigating partly in the dark, trusting models that the sun itself seems intent on rewriting. Voyager 1's journey delivered a measurement that has quietly upended a fundamental assumption. After traveling for over 35 years, the hardy spacecraft crossed the heliopause in 2012, finally leaving the sun's protective magnetic bubble and entering the true interstellar medium. For the first time in history, humanity had a direct sensor placed in the galactic environment, able to measure the cosmic rays that have not been filtered or distorted by the sun's influence. This pristine data is called the local interstellar spectrum, and it was supposed to be the ultimate calibration point, the ground truth against which all our models of cosmic ray propagation could be tested. Instead, it created a profound enigma. The spectrum Voyager 1 measured just outside our door does not perfectly match what our best models, built from decades of data gathered inside the heliosphere, predicted it should be. There is a discrepancy, a subtle but stubborn mismatch in the numbers and energies of the particles. It is as if you spent your whole life studying shadows on a wall to understand the objects casting them, and then finally stepped outside to see the objects themselves, only to find they were shaped slightly differently than you had deduced. This is not a trivial accounting error. The local interstellar spectrum is the starting gun for the entire cosmic ray story within our galaxy. To understand where these particles come from and how they travel, we must first know precisely what the raw, unfiltered population looks like as it arrives at the solar system's edge. Our models of galactic propagation, which trace cosmic rays back from Earth to their possible sources, all depend on this initial condition. If our baseline measurement is off, even by a little, then every calculation that follows is built on a shaky foundation. Reconciling Voyager's direct measurement with our indirect models is therefore a fundamental calibration puzzle. Scientists are now forced to ask difficult questions. Have we misunderstood how cosmic rays are modulated or changed during their final approach through the heliosphere? Could there be a previously unknown, very local source of particles just outside the heliopause that is contaminating Voyager's pristine view? Or does the discrepancy point to a flaw in our understanding of how these particles diffuse through the tangled magnetic fields of the galaxy itself? Each possibility requires rethinking a different chapter of the cosmic ray saga. Voyager 1's lonely beacons from the interstellar dark are not just a triumph of exploration. They are a cosmic correction, a quiet signal telling us that our map of the particle sea around us needs redrawing. Until we solve this calibration riddle, every story we tell about the origins of cosmic rays contains a hidden question mark, written in the data from a probe now over 15 billion miles from home. The same cosmic particles that may have sparked life now threaten to derail our most advanced technology. Quantum computers, machines that harness the bizarre rules of the quantum world, promise to revolutionize everything from medicine to materials science. Their power lies in quantum bits or qubits, which can exist in a delicate state of superposition, being both a 1 and a 0 at the same time. This fragile state, however, is exquisitely sensitive to interference from the outside world. For years, engineers have focused on shielding these systems from earthly noise, like vibrations and electromagnetic waves. But a startling discovery revealed an enemy from much farther away. Researchers at a leading quantum computing lab found that their superconducting qubits would occasionally and randomly experience catastrophic errors, flipping their state in an instant. After meticulously ruling out every local source of interference, they traced the culprit upward to the sky. The villain was not the primary cosmic ray itself, but the cascade of secondary particles, like neutrons and muons, created when that ray struck the atmosphere. These particles, raining down constantly, can zip right through conventional shielding and deposit a tiny burst of energy in the qubit. That minuscule energy kick is enough to collapse its delicate quantum state, introducing a critical error in a calculation. This transforms a fascinating astronomical phenomenon into a pressing, multi-billion-dollar engineering enigma. How do you build a practical quantum computer when the universe itself is constantly peppering it with error-inducing radiation? The first line of defense is brute force shielding. Laboratories are already experimenting with housing quantum processors deep underground, in old mines or beneath mountains, using hundreds of feet of rock as a natural cosmic ray filter. Others are designing advanced shields using layers of specialized materials like boron, infused concrete, or hydrogen-rich plastics to absorb the secondary neutrons. But perfect shielding may be physically impossible or so prohibitively expensive it renders quantum computers impractical for widespread use. This forces a profound shift in strategy. If we cannot stop the cosmic rain, we must learn to compute through the storm. This is where the mystery deepens into the realm of theoretical computer science. Quantum error correction codes are the proposed solution, algorithms that spread the information of a single logical qubit across many physical qubits. The idea is that even if a cosmic ray disrupts one or two of the physical qubits, the system can detect, and correct the error without losing the overall calculation. Yet, cosmic rays present a uniquely devastating challenge. Unlike random electronic noise, a single secondary particle striking a chip can create a burst of energy that affects not just one, but many adjacent qubits simultaneously. This correlated error, a cluster of failures from one cosmic event, is far harder for standard error correction codes to handle. It is the difference between a single typo in a manuscript and a spilled coffee cup blotting out an entire paragraph. So the cosmic ray threat is forcing a complete reimagining of quantum computer architecture. Scientists are now exploring topological qubits, which store information in the global properties of a material rather than a single vulnerable point, making them inherently more resilient. Others are designing new error correction codes specifically tailored to identify and fix these clustered bursts of cosmic ray damage. The enigma is no longer just about particle physics. It is about the future of computation itself. Can we outsmart the universe's own randomness? The success of the quantum age may depend not just on brilliant engineers, but on our ability to decode and deflect the invisible messages from the stars that constantly whisper through our machines. Even as we shield our quantum machines from cosmic rays, a daring spacecraft is flying straight toward their source. The Parker Solar Probe is an engineering marvel, a mission designed to touch the sun. Protected by a revolutionary heat shield, it plunges through the sun's outer atmosphere, the corona, where temperatures soar to millions of degrees. In this inferno, its instruments have recorded a particle phenomenon that has left solar physicists utterly bewildered. The probe detected sudden, intense bursts of incredibly energetic particles, events that dwarf the steady stream of the solar wind. These are not the predictable spikes from massive solar flares. They are something entirely new, erupting in seemingly calm regions of the corona, where our models said such violent acceleration should be impossible. Imagine a tranquil pond suddenly shooting out geysers with the force of a fire hose, for no apparent reason. That is the scale of the mystery unfolding just 93 million miles away. These particle blasts are rewriting the textbook on our nearest star. For decades, we thought we understood the sun's primary particle accelerators. Giant solar flares, caused by the snapping and reconnecting of magnetic field lines, were the obvious culprits for creating sudden surges of high-energy electrons and ions. The steady solar wind was a gentler, constant flow. The Parker probe's data reveals a third, hidden channel of acceleration operating right in the sun's atmosphere. The leading theory points to a process called magnetic reconnection, but on a miniature, pervasive scale. Instead of the colossal explosions of a flare, the sun's corona may be crackling with countless tiny magnetic explosions, nanoflares too small for our telescopes to see individually. Each one by itself is insignificant, but together they could act like a cosmic popcorn machine, constantly popping and collectively accelerating particles to unexpectedly high energies. This discovery suggests the sun's corona is not a smooth, hot gas, but a seething, nano-explosive plasma, perpetually injecting energy and particles into space. The implications of this reach far beyond our solar system. If such efficient, small-scale acceleration is happening routinely in the sun's relatively tame magnetic environment, it forces a radical rethink of the monsters we suspect across the galaxy. The processes Parker is witnessing in our stellar backyard could be the fundamental blueprint, operating at a mind-bogglingly larger scale and power elsewhere. The magnetic reconnection and turbulent plasma physics that create these bizarre particle bursts near the sun could be the very same mechanisms, supercharged by the immense gravity and magnetic fields of a supermassive black hole that launch relativistic jets from active galaxies. A microsecond magnetic snap on the Sun might be a scaled-down version of the engine that can accelerate a proton to become an oh my god particle. The Parker Solar Probe, by flying into the furnace, has given us a front row seat to the universal rules of particle acceleration. It shows us that the universe does not need a single, catastrophic explosion to create high-energy rays. Sometimes, it is the ceaseless, whispering fury of a billion tiny sparks that builds the fire. From the sun's whispering corona to the vast emptiness of the Boots void, these 25 enigmas form a single, sprawling map of our ignorance. They are not just a list of curiosities, but a living frontier. Each one, from the oh my god particle that defies cosmic horizons to the subtle dance of solar modulation that guards our technology, is a probe sent by the universe itself. These high-energy messengers are conducting experiments in physics we cannot replicate, testing the laws of reality in regimes of energy and scale beyond human engineering. They are the universe's way of asking us the hardest questions about its own structure, composition, and history. The true story of cosmic rays is not about particles raining down. It is about the questions they carry up from the void. They force us to look at empty space and wonder what monsters it hides. They make us reconsider whether the climate of our world is written in the stars, and if the spark of life began with a subatomic bullet. They challenge our most advanced machines and our most fundamental theories. Every mystery we have explored is an open door. The hunt for the first confirmed Pevatron continues. The debate over dark matter's signature in the positron excess grows sharper with each new data point. The next Amaterasu particle could be striking the atmosphere right now, its arrival silently recorded in a desert detector, waiting to point us toward a new cosmic nowhere or reveal a flaw in our most cherished physics. This is a detective story where the clues fall from the sky, and the case is never closed. So stay curious, look up at a clear night sky, and remember, it is not empty. It is filled with invisible, high-energy riddles, each one a piece of a puzzle that stretches from the birth of life to the fate of the cosmos. The next great detection could happen at any moment, rewriting a chapter in our understanding. Which of these 25 mysteries left you the most awestruck? Let us know in the comments.